Let's look at an example involving the trapezoidal rule. In your notes, you'll see an estimation of error. That is, if you use the trapezoidal rule to approximate a definite integral, you have an upper bound on the error, and that's the b minus a cubed divided by 12n squared, where n is the number of subdivisions. The a comma b just defines the interval of integration here. And then you have the maximum of the second derivative. That is, you can make an estimate of this if necessary. So this is an upper bound for error. Now in the next section, we're going to define the natural log function, but this makes a really good example for this particular estimation rule. The natural log of 2 can be defined as the integral from 1 to 2 of 1 over x dx. Now, the integral 1 over x is one of those interesting integrands that doesn't work with the power rule that we understand. You know, we add 1 divided by the new power, but when the power is -1, that doesn't work. That gives us something that is undefined. So this definition is very much needed, but you don't even need to know much more about it just to do this problem. So again, for AB, we have 1, 2, so b minus a is 1, and f of x is 1 over x. So in our theorem, we need to get a handle on the second derivative. So we have f prime will just be negative x to the -2, just using the power rule. And then of course f double prime will be 2 times x to the -3rd. And say we want to guarantee an error of less than 1 over 10,000. So what we need to do is to determine via this term an appropriate n. So for instance, let's just go ahead and fill everything in. We'll have 2 minus 1 cubed divided by 12n squared, and we need the maximum on the closed interval 1 to 2 of 2 over x cubed in absolute value. Well, this is a decreasing function, so we have to look at this at the sense that if it's decreasing, it will be maximized when x is smallest, so when x is 1. So what we have here is 1 over 12n squared times 2. That is, when x is 1, we get 2 as a maximum. And we want, well, as you reduce this, we want 1 over 6 times n squared to be less than 1 over 10,000. So this is elementary. We can divide out the 2's to get 1 over 3n squared less than 5,000, and then reciprocate. So we'll have 3n squared greater than 5,000, and then division by 3, and then assuming that we have a positive number of divisions, this would imply that n must be greater than the square root of 5,000 divided by 3, which is approximately 40.8. So if you want the 4 decimal place accuracy, you need subdivisions of at least 41. So the actual process of writing the trapezoidal rule is not difficult. When you have lots of subdivisions, it's probably in your best interest to write a subroutine that can do some of the computation for you. But for instance, let's just say that we're interested in applying the trapezoidal rule when n is equal to 41. So we're going to have these nice regular subdivisions. So we have an interval length of 1 here, and we divide 1 by 41. So A and B, we know 1 and 2, and then we just increment by 1 over 41. So we get 42 over 41, 43 over 41, 44 over 41, etc. So when we get to the x of I minus 1, this is just 1 plus I minus 1 divided by 41, and the x of I will just be 1 plus I divided by 41. And of course, these could be your evaluation points, just like doing the limit of a sum. And then as we move through, we have 81 over 41, and then to 82 divided by 41, which is 2. So there are 42 elements in this partition, which make 41 subdivisions. So if you're interested in using a particular approximation technique, namely trapezoidal rule or even the Simpson's rule, you can do a little bit of work ahead of time to see how many subdivisions you need for a particular decimal place accuracy. And this is very valuable technique. And we are done.